Okay, so today we're going to have a look at molar volume. Now, we went through this in our live session, but I'm just going to flick through this again. If at any point you want to copy the slides down, it's entirely up to you. You're higher pupils now. You decide what notes you want to take. I'd suggest you making some notes, but it's entirely up to yourself. And you just pause the video and make whatever notes you wish. So we're going to be learning about calculations using balanced equations and gas volumes. It's all based on the same stuff that we've been doing up to now. But first of all, I'm going to tell you all about this molar volume and mole thing, which blew my mind when I was your age. So basically I had two guys, Avogadro and Loschmidt. And it was Avogadro that said, basically a mole of any gas at constant pressure and temperature fills the same volume, right? So the same number of moles of any gas gives you the same volume, and at room temperature that volume just happens to be 24 litres, right? Loschmidt then says, well, he worked out that a mole is actually 6.022 times 10 to 23 atoms, and we ended up giving that number a name. We called it Avogadro's number, right? Yeah, which seems a bit unfair. So essentially what we're saying here is that it doesn't matter what gas we're talking about, if you've got the same number of moles or the same number of molecules, if you like, because remember, moles is just a large number. So if you've got a dozen molecules of any gas, it will fill the same volume as any other gas. If you've got 24 molecules, if you've got 40,000 molecules, if you've got 6.022 times 10 to the 23 molecules, in other words, a mole of molecules, it will fill exactly the same volume from gas to gas. It doesn't matter which gas you're talking about. So this could be 1 mole of hydrogen, or it could be 1 mole of butane. But remember, that's dependent on the temperature and the pressure. If you increase the temperature and the pressure, or you increase temperature, decrease pressure, that volume will change. So lower temperature equals less volume. Now, I'm just looking at that as I'm saying it. Lower pressure will give you less volume, but of course lower pressure will give you more volume, right? So if you decrease the pressure, the molecules can move further apart. That'll give you a greater volume. So that slide's not entirely right. Okay, but you can have a wee think about that yourself. This stuff is it's very important for you to stop and listen to things I'm saying, and then try and make sense of it for yourself. Yeah, have a think about it. Look up the internet, look up textbooks, chat to one another, try and work it out. Okay, so a mole of methane at room temperature and pressure is going to be 24 litres. What volume does 0.5 moles occupy? Well, it's going to be half of that, isn't it? 12 litres. What volume does 2 moles occupy? It's going to be double that, 48 litres. How many moles in 12 litres? Well, if there's 12 litres, that's only half a molar volume, so it's half a mole. What about 4 litres? Well, that's a sixth of a molar volume, so that's a sixth of a mole. Yeah, and it starts to get more complicated, doesn't it? So if we were asked the question, what volume does 0.735 moles occupy? Well, you can't do that in your head. You've got to do it using a equation, and like all good equations, they fit nicely into a triangle. And we can see here that the number of moles is the volume in litres divided by the molar volume in litres. So in this case, the volume, that's what we're trying to work out here, is equal to the number of moles times the molar volume, which is 0.735 times 24. That gives us a volume of 17.64 litres. Yeah. Now that makes sense, because surely if you look at that number 0.735, well, 0.735 is about 70% of 1. So we're talking about 70% of 24 litres, which is, 17.64 litres. Okay, let's actually look at a proper example here. So in some instances, you're given volumes in the question. When this is the case, you can think of it as just being told about the moles, right? And you simply compare the molar ratio then. So here's an example. If 500 centimetre cubed of reactant A is reacted with reactant B on a 1-to-1 molar ratio, 500 centimetre cubed of reactant B will react, because the molar ratio is 1-to-1, right? And the molar volume is the same for every gas. Doesn't matter. So basically, if you've got 500 centimetre cubed of reactant A, it's going to react with 500 centimetre cubed of reactant B, because it's a 1-to-1 molar ratio. Look at reactant C. Product C. That's a 1-to-1 ratio with A and B as well, isn't it? So you're going to get 500 centimetre cubed of C produced. But what about D? Look, that's a 1-to-2 ratio. So whatever you've got in A or B, you have to double it for D. Yeah, so it's 1,000 centimetre cubed. Okay, here's an actual type of question. Let's consider this one. 100 centimetre cubed of nitrogen reacts in excess hydrogen to produce ammonia gas. That means we've got 100 centimetre cubed of nitrogen in total, but we've got as much hydrogen as you need, right? Loads of it. So what volume of hydrogen would actually react, right? What volume is going to react with that 100 centimetre cubed of nitrogen? Well, it reacts on a 1-to-3 basis, doesn't it? 1-to-3, because the molar ratio here is 1-to-3-to-2. So for hydrogen, it's 3 times the volume of the nitrogen, so that's going to give us 300. What volume of ammonia will be produced? Well, that's a 1-to-2 ratio with nitrogen. So if it's 100 for nitrogen, it's going to be 200 for the ammonia. So this time, instead of it being 300 centimetre cubed of nitrogen reacting with excess oxygen, what we're saying here is we've got a finite amount of hydrogen. We've got 1,000 centimetre cubed of hydrogen. So 300 centimetre cubed of nitrogen reacting with 1,000 centimetre cubed of hydrogen to produce ammonia gas. Just apply exactly the same thing again. What volume of hydrogen would be used, or what volume would react? Well, 3 times what nitrogen of the nitrogen you've got, 3 times, because it's a 1-to-3 ratio. So, go back. So, what's 3 times 300? That's 900, isn't it? So, for A, the volume of hydrogen that's going to be used is 900. What volume of hydrogen would remain unreacted at the end? We always started off with 1,000. We've reacted 900. So you're going to end up with 100 at the end, left over, unreacted. What volume of ammonia will be formed? Well, it's a 1-to-2 ratio with the nitrogen. So you're going to form 600 centimetre cubed of ammonia. And what will be the final volume of gas mixture at the end? Well, you've used up all your nitrogen. You've got 100 centimetre cubed of hydrogen left, and you've produced 600 centimetre cubed of ammonia, so you've got 700 centimetre cubed in total. And the best way to do this, I think, is just in a little table. So basically, what you do is you write down your balanced equation, then your molar ratio, and you write down everything that you've got before the reaction starts. So the question said we had 300 centimetre cubed of nitrogen and 1,000 centimetre cubed of hydrogen. Then you write down what's happening during the reaction. Well, 300 centimetre cubed of nitrogen is reacting with 900 centimetre cubed of hydrogen to produce 600 centimetre cubed of ammonia. After the reaction, all of your nitrogen has been used up. 900 centimetre cubed of your hydrogen has been used up. That leaves 100 centimetre cubed of hydrogen left over. And you've got your 600 centimetre cubed of ammonia that was produced. So if you just wrote that down, you've answered the question, A, B, C and D. Because there is the composition and the volumes of the gases left over at the end of the reaction. 600 centimetre cubed of product is ammonia and 100 centimetre cubed of unreacted hydrogen. So this is one that I got you to try on your own. I'm going to actually put a little another little video up of me doing this on paper, but hopefully you'll be able to give this a good shot yourself. And then I've got an assignment for you to do with I think there's 10 examples of questions to try. Okay, right, well, best of luck guys, enjoy it, and have a good week.